Just while we're waiting, we are starting to recruit the next year, and we are inviting year 10 to join COMPOS. So we have a new program for year 10, which we're in the process of making. So if you could all tell your teachers that about us, and if they don't know already, and say that we are recruiting. Registration is open for year 10s and new year 12s, of course. So yes, year 13 would probably be reserved for you guys, because there's a lot of you, and we don't have we have just over 100 places for year 13. So
hi Vlad.
Hello. Hi David. Yes. So just saying that we've started registering students for the next year. So happy to accept. And we do have more places for private school students. So that's another thing.
Oh, I'll start advertising it to my school, although I can understand why you might prioritize state school candidates.
Well, well, yes, obviously, but we have paid places for private school students.
That makes perfect sense.
So this is not part. This is called COMPOS Foundation. So it's a parallel course, but it's very closely connected with the main COMPOS program.
And we're doing combinatorics today.
Absolutely. Well, to you, David.
So am I ready to start?
Yep.
Excellent. Sorry I'm a little bit late. Zoom just made me update my software, and I'm just hoping that doesn't create any gremlins. Hopefully it will make Zoom just run better. I'm just going to share my screen, and I'm going to start with a wonderful combinatorics question from a Matt paper, which I think is a really good illustration of some of the ideas. I'll then do some slightly more basic examples. And then, having done those slightly more basic examples, I'll go through the sheet that you've been working on. In the meantime, if you've got any requests, if there's anything that you would particularly like to go through, then just put those into the chat. But let's start at the very top. Let's start with a wonderful question from a Matt paper. So this is question number 6 from 2020. And I think this is such a good question because it's got so many ideas contained within it. In fact, I think it's probably got all of combinatorics within it.
Sorry, are you sharing your screen?
It says that I am. No, sorry, there was one more. It required one more OK. I think I am now. Super. So it says the cancellation of the Wimbledon tournament has led to a world surplus of tennis balls, and Santa has decided to use them as stocking fillers. He comes down a chimney with N identical tennis balls, and he finds K named stockings waiting for him. Now, this is where I want you to warm up your brains and warm up your powers of explanation, because I really want to zoom in on these two words, identical and named. Okay. Now, at first glance, these are sort of slightly strange. These are not what is, it's not immediately obvious what their significance is. So can anyone in the chat explain the significance of identical and named, and how that influences how I need to treat the tennis balls and the children differently? No one's putting anything in. No one's. We've got a first. Right. All tennis balls are the same. The stockings are all different or labeled. So the stockings must be treated differently. Right. Okay. I really want to. Maybe it's difficult from the chat, and maybe it's just something which I need you to sort of engage with at this point. To explain how we treat them differently. So let's imagine that we've got 3 children. Oops. And I'm going to name the children A, B, and C. So I've got child A, child B, and child C. Because the balls are identical, what this question is telling me is that it's only important how many balls each child gets. So if child A gets 3 balls, child B gets 2 balls, and child C gets 1 ball, that counts as one arrangement. Okay, now what doesn't matter, and what child A doesn't care about, is he doesn't care which 3 balls he gets. Okay, so the question would be quite different if the balls had been numbered. Okay, so if the question had said he comes down the chimney with n numbered tennis balls or n named tennis balls, then a sort of unique arrangement wouldn't just be child A getting balls, 3 balls. It would be child A getting balls 1, 2, and maybe 4, and child B getting balls 3 and 5, and child C getting ball 6. That would count as an arrangement, and that would be a different arrangement to if child A, if you swap the balls over. So if child A had balls 1, 2, and 4, and child B had balls 3 and 5, that would be different. Okay. So the fact that the balls are identical means the children do not care which balls they get, so you're only interested in the number. But what's significant about the stockings being labeled? Well, the fact that the stockings is labeled means that we do care which of the children get 3 balls, which of the children get 2 balls, and which of the children gets 1 ball. So, for example, this allocation that I've just had of child A getting, child A getting 3 balls, that is not the same as allocating 1, 2, and 3 balls to different children. Okay, what's the purpose of this discussion? Well, what it means is that in a real combinatorics question, like a map question, the first question you should always be asking yourself is, you know, what counts as a different arrangement? You know, and classic questions are, does order matter? Okay. You know, are objects labeled or not labeled? Combinatorics questions, for many of you who might be applying to universities like Oxford or Cambridge where they interview, combinatorics questions are very common within interview. And sometimes you know, if an interviewer doesn't specify, sometimes they might not even give you enough information in the way they ask the question, because they're looking out to see if you think about issues like this. You know, that if you just say how many different arrangements are there, you have to ask the question, what counts as different? Okay, let's proceed further with the question, and hopefully you're reading a little bit ahead of me as well. So it says, let GNK be the number of ways that Santa can put N balls into K stockings. For example, G22 equals 3, because with 2 balls and 2 children, Miriam and Adam, he can give both balls to Miriam, both to Adam, or he can give them 1 ball each. So we've got GNK, and it's just worth making a little mental note here that that's N children and K balls. Okay, we've got a couple of 1 markers here, and to sort of, I suspect that these are answers which you really should just be able to write down the answer and put it into the chat. What is the value of G1K? Okay, so you've got 1 child, sorry, it's the other way around. It's N balls and K, sorry, it's N balls and K children. Okay, so the question asks, what's G1K? So how many ways can you put 1 ball, can you allocate 1 ball to K children? And then what's the value of GN1? Okay, and you should just be able to put both of those in the chat. If you're feeling super keen, give an explanation, but otherwise just put the number. Yeah, K and 1, excellent. Because, okay, if we've got K children, okay, so we've got child 1, child 2, child 3, all the way up to child K, and we're allocating 1 ball. It's just a simple matter of which child gets the ball. So I'm going to give it to child number 2. Okay, so G1K is just equal to K. GN1, however, is a very boring case because you've just got N balls, but you've only got 1 child, so you're forced to give all the balls to that 1 child. So there's just 1 way. Right, part II is important idea number 2 from this question. We saw at the beginning that we should always look at ways that are different. Part III is leading us towards a recursive approach to this problem. Okay, and recursion turns out to be incredibly important within combinatorics. So what do I mean with recursion? Well, it means this idea of using answers which you found previously to count new cases. Recursion and induction are virtual synonyms of one another. So it gives us a little bit of a hint of how to do this recursion. So it says if there's N greater than 2 balls and K greater than 2 children, then Santa can either give the first ball to the first child, then distribute the remaining balls among all K children, or he can give the first child none and distribute all the balls among the remaining children. Use this observation to formulate an equation relating the value of GNK to other values taken by G. Okay, and this is actually giving you a lot of structure to help. So let's consider those 2 cases. So we want to consider GNK, and that's N balls and K children. Now, Santa can take the first ball and give it to the first child. He then has N minus balls left to distribute, and there's still K children he can give them to. The number of ways he can do that, because we've reduced the number of balls, is G N minus 1 K. The other option, so I'll just annotate what this is. So this is allocating it's not letting me write. This is allocating the, sorry, my pen is a little bit, but this way Gn minus 1k is allocating the remaining n minus 1 balls to all of the k children. The second case would be where he gives the first children none, and then he distributes all the balls. So in that case, there would still be n balls. But now, because he's not using the first child, there's only k minus 1 children. So this first case was child 1 gets ball 1. And this second case, or these second cases, are when child 1 gets no balls. And I probably shouldn't say ball 1 gets 1 or more balls. A ball. Okay, so we get this recurrence relation. Right, again, just a little bit of time to put something into the chat. Where do you think you've seen this recurrence relation before? And how do you think you've now got enough information to tackle part IV? So two-part question, put into the chat any thoughts that you've had of when you've seen a relationship like GNK equals GN minus 1K, GNK minus 1 before. And then also put into the chat what method you would use to find the value of G75. Well, I think I'll leave it as a little bit of suspense of what this recurrence relationship is a little bit like, but the method that we now use is an inductive method because these values over here tell me that I know what to do for G1k. So if the first argument of the function is 1, I know what to do. If the second argument of the function is 1, I know what to do. Gn1 is 1. And then this recurrence relationship will allow me to climb to higher values. So let's put the two together. And the natural thing to do would be to form a table of values. So let n, the number of balls, go from 1, 2, 3, 4, 5. And I only need to count up to 7. And then the number of children can go 1, 2, 3, 4, and 5. And now I can simply make some sort of grid. Okay, what I found is that if k is 1, then regardless of what n is, there's only one way of allocating the balls. So this first row is always 1. However, if there's just one ball, then the number of ways of allocating it is the same number of the children. So I've got this row here. Now, what does my recurrence relationship tell me? It tells me that GNK is GN minus 1K. So that is the value to the left of the unknown value, plus GNK minus 1, which is the value above it. So if I want to find the value in this empty square here, I just add the 2 and the 1, and I make a 3. To find the value here, I add the 3 and the 3, and I make a 6. Here, I add the 3 and the 1 to make a 4. Here, I'm adding the 4 and the 1 to make a 5. Here, I'm making a 10. Here, I'm making a 10. And now I'm going to put this out there in the chat. And I think, does anyone recognize the pattern of numbers that is emerging? So where have we seen numbers like 1, 1 and 2, 1, 3, 3, 1, 4, 6, 4, and so forth? And while I'm waiting for the answers to come into the chat, I can continue finishing this grid. And by the time I finish this grid, I expect to see everyone put the answers in, because this is, when it comes to counting, this is the most famous family of numbers of all. 56 plus 28, 64, 84, 126. The numbers are getting a little bit large. 130, 210, 126. I'm getting 336. And I may have made a mistake, but I can check that mistake later. Let's go into the chat. Oh, and people are saying it looks like Pascal's triangle. Well done to all the people who put that into the chat, that it looks like Pascal's triangle. It is Pascal's triangle. Okay, let me now zoom back of why I chose this math question as such a good one to do. And I chose it for I chose it for several reasons. One, it had this useful bit at the beginning of this, where you needed to distinguish between what was meant by a different object in terms of counting. I also chose it because of recurrence relations. But I also chose it because now that Pascal's triangle emerges, that is a bit of a hint, okay, that I might have been able to find a direct way of finding G75, which didn't require this recurrence relation, but instead found an argument to show why the numbers I obtain here are the same as Pascal's triangle. Okay, and this happens a lot in combinatorics. You count something, you suddenly realize, oh, this is Pascal's triangle, or this is, you know, some other pattern of numbers that I recognize. And then you think, right, could I have transformed this problem and thought about it in a different way, where I could have just immediately just noticed that it was actually the same problem that is counted by Pascal's triangle. So let's have a look at now finding a direct proof. Notice this wasn't asked for in the map question. The map question part V, which we'll look at later, just does a minor tweak of this problem. But let's look at an alternative approach to this problem. So let's imagine I wanted to find G33. So this is 3 balls and 3 children. The first thing I'm going to do is I'm just going to divide my page up into sort of 3 sections. Okay, the section that's going to belong to child A over here on the left, the section that is going to belong to child B in the middle, and the section that's going to belong to child C on the right. And now I'm just going to allocate 3 balls in some way. So I'm going to give child B 2 balls and child C 1 ball. Or alternatively, okay, I could have given child A 3 balls and then sort of given child B and C nothing. Can anybody in the chat, or alternatively, if you're watching this on catch up, pause the video and have a think. Can anybody think why, just from this little sort of scribbly drawing that I've done now, how I can transform and translate this problem of allocating balls to stockings, why I can translate it to Pascal's triangle and those famous counting numbers? I mean, I'll give you a little bit of a clue. Remember what those counting numbers count. So, for example, if I was to have tossed coins and I tossed a coin 5 times and I knew there were 2 tails, the number of arrangements would be 5C2. The number of ways of picking 2 places from 5 places. How can I see a relationship between my ball allocating problem and my heads and tails problem? Okay, so people have put because it's like choose functions. Let's see why it's like choose functions. Okay, well, every allocation of balls corresponds to a pattern. Okay, now what pattern do I mean? I mean a pattern of 3 balls and then 2 markers. So, for example, this is the 1 ball each. The red markers are where I split between people. Okay, or I could do 2 balls to child A, nothing to child B, and then the 3rd ball to child 3. Now, what does this pattern consist of? Of 3, and I'm drawing symbols as a little black circle. So I've got 3 of these, and then what I've also got is 2 of these markers between them. So in total, I have 5 symbols. And 3 balls. So there are 5 choose 3 ways. Okay, and 5 choose 3, you can do the Pascal's triangle. It's 5 times 4 over 5 times 4 times 3 over 3 factorial, so it's 10. Okay, and let's just check the table of values that I've got over here. 3, 3, G33 is 10. Okay, easy question, I think. Which way of counting is better? Okay, is the recurrence relation, so finding this recurrence relationship and then filling in the grid, better, or is this direct method of proof better? I'll put it to a vote, but I think this is a rare example in maths where there is just categorically a better method. I'll just wait for some votes to come in.
Sorry, David. I realized that when I transferred the host rights to you, my recording stopped.
Oh no!
Could you allow me to record, or better if you could record?
Yeah,
Would that be easier?
absolutely happy. Oh dear.
Yeah, that's.
It was. It's going to be hard for people following live to leap into the end of this question. So let's. Is it recording now?
Yeah, it says recording.
Ah, excellent. Ah, it says recording. Right, excellent. Okay. I don't know what we're going to do about that and whether we're going to just need to trim the beginning of the recording, but we'll record what we can. For the benefits of the people just joining the recording, I have been working through MAT 2020, question number 6. I've worked through it the way that the question intended me to, which was to find a recurrence relation. And then using the recurrence relation, I generated very familiar looking numbers like 1, 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 5, 10, 10, 5, which looked like Pascal's triangle. Inspired by that, I found a different way of approaching this problem that led to a direct method of proof where I could just write down why the correct answer was a number from Pascal's triangle. And then I just thrown it out to the vote, which of these two methods is better? Okay, so if you preferred the recurrence relation, so finding that GNK equals GN minus 1K plus GNK minus 1, indicate it in the chat. If you prefer the direct proof, indicate that in the proof. Oh, interesting. Huh. Okay. I thought everybody was going to say direct. Interesting. I would agree that the recurrence relation is the one which is like easier to think of. And I think when you do counting problems for real, recurrence is really, really, really powerful. But I would have voted for direct proof. And the reason I would vote for direct proof is because I think it's slightly more powerful, but also in the context of this question, it just generalizes so nicely. So for example, here I got a direct proof of saying that G33 is 10, but I can do a lot better because I can say that if I had n balls and k children, so if I wanted to find GNK, so n balls and k children, the only thing I need to be careful of is how many dividers do I need? Well, if I just put in one divider, that splits the world into 2 halves. 2 dividers splits it into 3. So to split it into k stockings, I need k minus 1 dividers. And then every allocation of balls is just slotting in n balls in and around those k minus 1 dividers. And notice there might be some gaps where there's no balls. So now how many ways are there of making, choosing the position of the n balls in this list? Well, in total, I've got n plus k minus 1 symbols, and I'm just choosing the position for n balls. And so I think the direct proof gives a nice, easy way of generalizing this problem and just getting a very simple formula for what I would write down. If I do it the recurrence way, I would need to have a proof by induction to explain exactly why I get Pascal's triangle. And just for the sake of completeness, we should look at the last part. And I really like this last part as well. This question, by the way, when it was released in the MAT, had a little bit of ambiguity, and candidates interpreted it in two different ways. I'm going to interpret it in the way that I think the question setter suggested. So it says, after the first house, Rudolph reminds Santa that he ought to give at least one ball to each child. Let HNK be the number of ways of distributing the balls according to this restriction. What is the value of H75? So now Santa's got 7 balls that he's allocating to 5 children. But after the first house, so my way of reading this is that Santa can do anything he likes in the first house. Okay. So for part 5, we need to split up into the 2 cases. Oh, my computer's gone a little bit funny. We need to split up into the 2 cases of whether the first child gets a ball or not. So let's do that. Sorry, my computer froze. I'm just going to snip the question so I can refer to it. Okay, so let's split into the 2 cases. Case 1 okay. Could be that the first child gets no balls. Case 2 could be that the first child gets 1 ball. And case 3 could be that the third child gets, the first child gets 2 balls. Now let's think about why this question caused a little bit of ambiguity. The first thing to note is that if the first child gets more than 2 balls, then this H75 means allocating 7 balls to 5 children. Now, if the first child has got more than 2 balls, Santa's got fewer than 5 balls to allocate to the remaining children, and so that the problem is impossible. Okay, so when Rudolph reminds Santa that he ought to give at least 1 ball to each child, Santa can't do it. Okay, now the reason this problem caused a little bit of ambiguity was, does it mean that Santa is allowed to give 0 balls to the first child? So I'm going to interpret it as being that Rudolph's reminder to Santa applies after the first house. So 0 balls to the first child is possible, but 0 balls to any subsequent child is not possible. So let's consider what remains, what is left in the 3 cases when the first child gets 0 balls, the first child gets 1 ball, the first child gets 2 balls. So if the first child gets 0 balls, Santa has got 7 balls left to allocate between 4 children. Sorry, the first child can get up to 3 balls. In this second case where the first child gets 1 ball, Santa has got 6 balls for 4 children. In the third case, there's 5 balls remaining for 4 children. And then in the final case of child 1 getting 3 balls, there's 4 balls for 4 children. Now it feels like we've now got lots of work to do because we've got to count each of these different cases. But the important idea in part V is that we can turn this new problem back into the old problem. So we can turn this problem where Santa needs to give at least 1 ball to each child back into the case where that restriction didn't exist. Why? Because if Santa needed to allocate 7 balls to 4 children, and each child needs to get at least 1 ball, Santa is forced to give those 4 children a ball each. So that takes up 4 balls. And then all that is left that Santa has got left to deal with is how to allocate the remaining 3 balls. But the number of ways of allocating 3 balls to 4 children is what we've previously called G34. By the same reasoning, if Santa is allocating 6 balls to 4 children, but each child must get a ball, the only ones where Santa's got a free choice, is, having given each child 1 ball, is the remaining 2. So that's G24. And then we've got G14. And then we've got a bit of a funny one, G04. How many ways can Santa give 0 balls to 4 children? Well, that's clearly 1. Okay, we can see that the answer here is going to be 1 because the only way to give 4 balls to 4 children is to give each child 1 ball. So we've just got +1. So we need to add 1 to G14, G24, and G34. And all we need to do there is go back up. We can just simply go back up to our table. So K is 4, and we're adding these 3. This is the 4, the, doing a different color, the 4, the 10, and the 1. So we just do 1 plus 4 plus 10 plus 20. And that gives me 35 ways. An alternative way of interpreting this question, which ended up being allowed on the mark scheme, was that Rudolph's restriction is just that every child must get at least 1 ball, in which case H75 just becomes H25 because it's allocating the two extra balls. Okay, that's that math question dealt with. Does anyone have any questions, comments about the math question? If not, can you just put a thumbs up and I'll move on to looking at your sheet. And I'll just put the sheet into the OneNote. What's the name of the sheet? Sorry. Maths 12 PDF. Cool, we've got thumbs up in the chat. We've got a very nice comment in the chat from someone who compared the direct proof to the proof by recurrence. And I think I'll agree with this as the right sort of conclusion. So someone had written that he thought that the direct proof was more elegant, but the recurrence is easier to see. And I think there's a lot of truth in that. Okay, let's do some combinatorics questions. Does anyone have any, based on people looking at the sheet, are there any problems that people would like me particularly to look over? No? In which case, I'm going to look at question number 7. Okay. So CNK is equal to NCK minus 1. Now, in each case, I'm going to try and present 2 proofs. And the 2 proofs I'm going to present are a formula-based proof and a counting-based proof, and perhaps a binomial theorem-based proof as well. But for 7a, the formula-based proof is easy. Okay, NCK, there's just a nice formula for it. It's n factorial over k factorial n minus k factorial. Now, if I just plug NC n minus k into this formula, I still get n factorial on the top. Where I had the k factorial, I've now got n minus k factorial. And then if I take n minus k, the other factorial is just k factorial. So that seems fine. That's the formula-based proof. What would be the counting argument? Okay, well, let's just go back to our heads and tails examples. Okay, so let's say that we've got n coin tosses and we've got k tails. Okay. So the number of n coin tosses with k tails is NCK. But did we need to count the tails? Okay, now some people like tails, some people like heads. It might be that we liked heads more than tails. So instead of thinking of n coin tosses with k tails, we could have thought of this as the same problem, but this is the same as n coin tosses with n minus k heads. But the number of ways of n coin tosses with n minus k heads is just choosing the n minus k from the n positions. So that's going to be n, c, n minus k. Okay, so it's just a symmetry argument. Okay, let's look at part D. Which says NCR plus NCR minus 1 MC1 plus NCR minus 2 MC2 plus ... MCR is equal to N plus MCR. Now, I would contest that, well, let's put this to a vote. Part A, I would argue, was very simply done with the formula. And doing a counting argument was much more involved. So for part A, the formula was probably the better method. And the counting argument was a bit more subtle. But for part D, look at it, okay, and picture yourself either using the formula or a counting argument. Which do you feel, just in your instinct, is going to be easier, the formula or the counting argument? Now, I would contend that the formula is just going to be horrible because there's going to be a sea of there's just going to be a sea of factorials flying around, and it's going to be very, very difficult. So let's try and do part D an elegant way using a counting argument. Now, the first thing to notice that the majority of the terms in part D see us counting from choosing from having an NCR term, which means choosing from a group of n, and an MCR or MCK term, which means choosing from a group of n. So if we think in those counting terms, we might be able to relate this to a problem where we're choosing a group from two types of people. Okay, so let's imagine that we have a group where there's two types of people. So let's imagine that we have n people with brown eyes. So n is we have a group of n people. So there's a group of n people. So there's a group of m plus n people. And n have brown eyes. And m have blue eyes. And I want to pick a group of R people. Okay, where does R come from? Well, I want the term that I ultimately want is this Cn plus MR. And now I think we can see where the counting argument is going to go. Okay. So if there are K, okay, so if there are K blue-eyed people, this can be done in how many ways? Well, if there's K blue-eyed people, I need to choose K people from this group of M. So I can do CMK ways of counting the blue-eyed people. I then need to complete the group choosing from the brown-eyed people, and that can be done in C, and then I need to pick a remaining R minus K people from the brown eyes. So this is the number of ways of K blue people from M. And this is the number of ways of N minus K. Oh, sorry, of R minus K brown-eyed people. So in total, okay, we just need to sum over the K, so we could choose no blue-eyed people, so that's just CM0, and is choosing all of the group from the brown-eyed people. Or we could choose one blue-eyed person in CM1 ways, and then pick everyone else from the brown-eyed, all the way up to picking everybody who's blue-eyed in CN0 ways. But if we now decide that we don't care, if we suddenly just decide, wait a minute, I don't care about eye color. If I just regard them, as people, if I ignore eye color, then the number of ways is just choosing R people from N plus M people. So it's just CN plus M, choose R. Okay, I'm going to make a little bet here at this point of what people are going to put in the chat about this method. Okay, so this is a counting argument for part D. So it's a little story. It's splitting the group into brown-eyed and blue-eyed people. Put in the chat whether you like counting arguments like this, or whether you prefer arguments that are more algebraic. So if you prefer algebraic proofs, write algebra. If you like counting proofs, write counting in the chat. Okay. Oh, and I was almost right. I suspected that everyone would say algebraic, but I did get one person who said they preferred counting. Okay. So I'm going to present an algebraic way. And this algebraic way is very useful to see in terms of the numbers involved in Pascal's triangle. But for more complicated examples involving the algebra of Pascal's triangle, we tend not to use the formula using factorials, but we tend to use the binomial theorem. So let's look at how the binomial theorem can give me this lovely identity in part D. So we're going to try and get the same identity. Now, the first thing we see is we know we want to get an expression for Cn plus Mr. Now, when are we going to get an expression for counting numbers with a sort of base of n plus m? We know using the binomial expansion that that's going to be related to the expansion of 1 plus x to the n plus m. Now, when are we going to get Cn plus Mr? Well, it's the coefficient of xr in this binomial expansion, 1 plus x to the n plus m. But then if we look at the identity that we're trying to make, which we want a identity which is going to involve n's and m's. But there's a natural way of splitting up 1 plus x to the n plus m. And that is writing it as 1 plus x to the n times 1 plus x to the m. Now, we want the coefficient of xr. Now, how are we going to get the coefficient of xr in this product? Well, what we could do is we could, instead of multiplying this together by combining the powers, we could use the binomial expansion in each bracket. So we would get 1 plus nx, and n is just a funny way of writing nc1. So then we've got nc2 x squared all the way up to ncn, which is just a funny way of writing 1 x to the n. And then we're multiplying that by the second bracket, 1 plus x to the m, and I'll write that second bracket in green, which is exactly the same thing. It's still the binomial expansion, but instead of having n choose 1, I've now got m choose 1. And then m choose 2. And then I go all the way up to m choose m, which is just x to the m. I'm sorry, I'm being a little bit inconsistent of whether I'm writing things as m choose something or whether I'm simplifying. But now the question is, what is the coefficient of x to the r? Okay, so how do I get a coefficient of x to the r in this product? And what I need to do now is just think about how I would expand out the bracket. So this 1, in order to get an x to the r term, I would want to multiply by CNR times 1. Because if I took an x to the r from the first bracket and it hit the 1, it would give me an x to the r term. The term that I would need to put with the term here that's got a coefficient of x is a term in the first bracket which has got a coefficient of x to the r minus 1, which is Cn minus 1. Sorry. Which is Cn not letting me change to an eraser, so I'll just scrub it out. Cn choose r minus 1, hitting the Cm choose 1 term. That would also give me an x to the r. I would also get an x to the r if I had Cn choose r minus 2, which is an x to the r minus 2 term in the first bracket, hitting an x squared, which is Cm2, all the way up to just having an x to the r term in the second bracket, which is CMR. So this gives the x to the r coefficient. And so that gives an algebraic approach. Now, in terms of like the maths that you do at university, this turns out to be a very fruitful and very beautiful kind of interplay, because what it shows is that sometimes you can use counting arguments to tell you things about algebra, and sometimes you can use algebra to tell you things about counting. Before I move on to the next question, I'll just do this as a vote. Put in the chat which of the two methods you preferred, the counting or the binomial expansion. And second thing to put into the chat, if you're happy with this question, just put a thumbs up and I'll move on and look at another question. Oh, we've got a vote for binomial. Another vote for binomial. And yeah, we got a unanimous set of votes for binomial. Interesting. I think that this is just because at school, you tend to do a lot of algebra and you tend to do less combinatorics. So as school leavers, your algebra tends to be typically nice and strong. So you prefer algebraic approaches. Right, let's have a look at some other questions on the sheet, and let's have a look at some probability ones. Okay, let's look at a good... Yeah, let's look at question number 16 from this PAT paper, 2015. So it says an unbiased coin is tossed 3 times. Each toss results in a head or tail, presumably with equal probability. And then it says, what is the probability of 2 or more tails in succession, that 2 consecutive toss results are the same, that if any of the toss results is known to be a tail, then all of the tosses resulted in tails. Okay. Despite the fact that this comes from a PAT quest paper, I'm hoping that everyone has got a good sense of how to tackle this problem. So what would be the most sensible thing to do? Well, the unbiased coin is tossed 3 times. So we can literally just systematically list the possibilities. So we could have heads, heads, heads. That comes alphabetically first. We could have heads, heads, tails. That comes alphabetically second. This exhausts every sequence which starts heads, heads. So then we need to get into the heads, tails world. Heads, tails, heads would be alphabetically first. And then we've got heads, tails, tails. That exhausts everything which starts with a head. So then we've got tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. Okay, you could also just get a similar systematic list from using a tree diagram. So what is the probability of 2 or more tails in succession? So for part A, all we need to do is decide which of the conditions meet this criteria. So 2 tails in a row are heads, tails, 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 heads, or tails, tails, tails. So that's 3 outcomes out of a possible 8. So the answer to part A is 3/8. Part B, what's the probability that 2 consecutive toss results are the same? Right, there's a cute way of doing this question, okay, which is barely worth doing. But a cute way is to note that the probability of having 2 heads in a row is going to be the same as the probability of having 2 tails in a row. And also, because there's only 3 tosses, that's going to be mutually exclusive, because you cannot have 2 heads in a row and 2 tails in a row. So you could just say that it's going to be 3/8 for having 2 tails in a row, plus 3/8 for having 2 heads in a row, and that simplifies to 3/4. But as I say, that's almost not worth doing, because you could just count up the outcomes, and it's everything apart from where you alternate. So apart from heads, tails, heads, and tails, heads, tails. So the answer to part B is 6 out of 8, which is 3/4. And then part C, it says, what's the probability that any one of the toss results, if any one of the toss results is known to be a tail, okay, so what that means is we know that there's at least one tail. What's the probability that all the tosses resulted in a tail? Okay, so there's still only one toss result, which is tails, tails, tails. But if we know that at least one toss result is a tail, we don't include the heads, heads, heads. Okay, so you could just write down that the answer is 1/7, because it's one outcome out of 7 outcomes that remain once you find out that at least one toss is a tail. What you could also do is you could use the formula, so the conditional probability formula. So the probability of all tails given at least one tail is the probability of both of these events happening, but because the intersection of all tails and at least one tails is the same event as all tails, the numerator just becomes the probability of all tails so my stylus stopped, oops. My stylus looked like it stopped working and then came back to life and just wrote a million times. So that's the probability of all tails on the numerator. And then we divide by the probability of at least one tail. So that becomes 1/8 over 7/8, and that simplifies to 1/7. Okay, are people happy with this probability example, problem 16? If so, put a thumbs up in the chat, and then I've got time just to look at one more, and I'll choose an interesting problem to look at. Excellent, thumbs ups. Morning. Okay, final problem of the day. Is we'll play the following game. So what we're going to do is we're going to keep tossing a coin. and I'm going to say player 1 wins if 2 heads in a row. Okay, so if heads is observed before tails. And again, my stylus is playing up. Okay, so player 1 wins if we see heads is before we ever see a tails. And player 2 wins if tails occurs before heads. Okay, I'm going to ask a question which, again, hits an important idea, but I hope you're just able to write down the correct answer without any thought. What is the probability player 1 wins? Okay, put the answer into the chat and a 1-word explanation. So what is the probability that the player 1 wins? So we just need to toss this coin, this fair coin, and if there's a heads before a tails, player 1 wins. Player 2 wins if there's a tails before a heads. Well, the probability that player 1 wins is just a half. And the answer is by symmetry. Okay, because heads and tails are sort of interchangeable because the probability is a half. So by symmetry, this is just a sort of fair game. What we're going to look at now, and I think this is quite a nice example to finish on, is we're going to ask a slightly more interesting question, is we're going to toss the first coin. And let's say the first coin comes up heads. And my question is going to be, what is the probability that player 1 wins if the first toss is a head? And what we're going to see here is that this question can be done in a sort of methodical way, which is doable, but it can be done in a much more elegant way if we use this magic idea of symmetry. Okay, and symmetry in counting problems becomes increasingly important. Right, I'm going to do it the sort of dull, methodical way. Then I'm going to gradually improve my dull, methodical way to get a more and more elegant way. So the first coin toss is just a heads. So we've got the head has happened. We can now start drawing a tree. And if the first toss is a head, then player 1 has just won. But if the first toss is a tail, the game goes on. Now there's 2 outcomes. After the first tail, there's 2 outcomes. There's a head or a tail. If the second outcome is a tail, then player 2 wins. If the second toss is a head, so if it went head, tails, heads, the game continues. And if it's a head, player 1 wins. Otherwise, player 2 wins. Sorry, otherwise it's gone heads, tails, and then we just need to continue the game further. So then there's a head or a tail. And then here, player 2 wins. And so on, we just need to carry on forever. Okay, so why does this tree end up being a little bit more problematic than most trees? Well, you end up with an infinite tree. Okay, so what bit of maths could you do to find player 1's way of winning? Well, if you just do it sort of naively with the infinite tree, you've got this branch where he just wins straight away. This branch where he wins after initial heads, tails. And then we've got this next branch where it goes heads, tails, heads, tails, and then it would be heads, heads up here. So the sort of most long-winded way is just to say he could win here on the first branch with probability 1/2. He could win the green way after a tail, head, head. And because that's 3 lots of a half, that's going to be probability 1/8. The purple way is 1, 2, 3, 4, is 1, 2, 3, 4, 5 ways. So it's another 3. So it's 1/32. What sort of maths is this? Well, this is just a geometric progression where we're going up by 1/4 each time. So we just need to sum the infinite geometric progression. The first term is 1/2. The common ratio is 1/4. So we just do 1/2 over 1 minus 1/4. And so that's 2/4 over 3/4. So that's 2/3. Okay, infinite geometric progression. Not hard, certainly doable. There's a slightly better way. Okay. Let P be the probability that we're trying to find. Be the probability that player 1 wins. I'm now going to show a little bit of symmetry to show how I can avoid the infinite tree. So again, we start with the heads that had happened at the beginning of time. We can then get an immediate heads or a tail. Then after the tail, we can get a head or a second tail. And in these situations, the game has just ended. Player 1 has either wins immediately or player 2 wins. But this is where at this point of the game, this is where this important idea of symmetry emerges. Because after this head, the fact that we've actually had the sequence heads, tails, heads just doesn't matter. Okay, that the player 1 is in exactly the same position as he was when the game started. So here and here is just the same. Yeah, the most recent toss was a head, and then player one will win if there's a head immediately, or if any tree which wins after the original head is just glued onto this second head. So these two positions, the starting position and this second head here, is the same. So instead of drawing an infinite tree, we can just say that the probability that player one wins is this P which we're trying to find. And now, rather than doing an infinite geometric progression, we can just do a finite thing, that the probability that player one wins, which is P, let's just sum over all the branches. So he could win immediately, just on the first toss, which happens with probability 1/2. Or he could win if we follow this branch. The first toss is a tail, the second toss is a head, and then he wins from that second toss, which was a head, which happens with probability P. And the probability of that purple branch is 1/2 times 1/2 times P, which is 1/4 P. And I hope you'll agree that that's more elegant, because we don't have an infinite geometric progression, we just have a finite bit of algebra. So we can say that 3/4 P is equal to 1/2, and then P is equal to 2/3. But now the most elegant of all, and this is going to be kind of symmetry, but even more symmetry. So we've again got our initial head. After the initial head, one of two things can happen. There could be a second head, in which case player one could win. Or there could be an initial tail. And this is where you might need to turn your brains up to full power a little bit. But after an initial tail, which player has the advantage? The player with the advantage is player two, because he just needs a single tail to win. So after this initial tail, player two has got an advantage. How big an advantage? Well, he's got as big an advantage as player one had after the original head. Because after we've got this initial tail, the probability that player two wins is the same that the probability that player one won after the original head. So these two positions, the starting position and the first tail, these two positions, they're equivalent but with the players reversed. So player two has become player one, the player with the advantage, and player one has become player two, the player who's got to do catch up. So what we know from this initial head, player two wins with probability P, which is player one's original probability of winning, and player one wins with probability 1 minus P. So what we can now write is that P is equal to 1/2 plus 1/2 1 minus P. And we get exactly, we then get exactly the same. Is that right? Yeah. Yeah. Because we now got P is equal to 1 minus 1/2 P, So 3/2 p is equal to 1, so p is equal to 2/3. Okay, so 3 ways of doing this problem. The long way with an infinite geometric progression, and then 2 ways with symmetry. Okay, and what we can see is that with symmetry, we've cut out the infinite geometric progression, and we've made the tree considerably smaller. Okay, so I'll finish with just this final observation that looking for symmetry in probability questions can often simplify them. So that's the end of time. Before I finish the meeting, I'll just go back to the main screen and just check if anyone's got any questions, if anyone's got any other things that they'd like me to look over, or if they're happy. If you've got any questions, just raise your hand using an emoji. If you're happy, put a thumbs up. I've got some thumbs up and some thank yous. Excellent. Thank you. Yeah, have a nice evening too. I hope you've enjoyed this webinar. Some nice problems. So we looked at the map problem to begin with, compared recurrence relations with direct proof. We looked at the importance of specifying in counting problems what arrangements count as different. We then did some nice work looking at the numbers in Pascal's triangle, comparing algebraic and formula-based approaches with counting approaches. And then we did this nice little game at the end. So have a lovely evening. I'm not sure if I'll see you all again before the summer, but if not, enjoy the summer and make sure that this summer is a summer really of preparation for, it's a golden opportunity to look at the COMPOS sheets, look at the map papers, look at PAT papers, and just do lots and lots of fun problems. So have a nice evening, everyone, and I hope to see you again. If not, have a lovely summer. Bye-bye.